Good afternoon, I'm Mr. Ish. Thank you for joining me. We've never talked about work with regards to integrals, but in this video we will. Very generally, many of you will know work is equal to force times distance. A certain force is anything applied to an object such that it can move it. When you move it over a distance, you've generated this concept of work. Work has newtons as the units for force and meters. You can say newtons, meters, or you can say joules as units for work. These are the accepted units, newtons, meters, or joules. I like to use the word joules. It's not a difficult concept to understand. If you have a certain function here which represents a graph, if you were to look at the area below the graph, this area below the graph here would equal to your work. Why would that be the case? Because if you were to plot your distance along the x-axis, you were to plot your force along the y-axis, you can think of everything here with regards to rectangles. A representative rectangle is being drawn. It would have a certain width, it would have a certain height. This certain height you can call length, this here you can call your width. The length over here would be your force component, your width here would be your distance component. When you multiply them, you're getting your force times distance. But if you add up all the distance and the force components for each of these rectangles, you sum them up, you get then the total accumulation. You know this figure f of xi and then delta x, all of that from 1, I is equal to 1 up to infinity, or you can say n is equal to 1 up to infinity. It doesn't matter how you want to say it, but that would give you your summation, and that summation would represent your work, which would be the area below the curve. We can do everything here with regards to a bunch of varieties of examples, but keep in mind you don't have to get that broad into this. Any physical phenomenon for which you can do force and there's a distance involved, you can bring that into this integral with regards to work. And your integral would be like this: work would be equal to a lower limit to an upper limit, your f of x. But here f represents your force component and dx. Anything which has a formula for which there's a force, mass times acceleration, you can bring over here. You can have kx, which is for the Hooke's law, you can bring it here. But I'm showing you how the work can be determined by means of an integral. The integral is you looking at things with regards to force and distance component, and you bring them together. We will look at a single question over here with regards to springs. Maybe in another video we can look at other forms of work questions, but this one has to do with the spring. And it has everything to do with the Hooke's law. It's very common for you to see something like this in calculus, Hooke's law. It has to do with this formula, force equal to kx. There's a certain constant here which relates to a spring when it's stretched. But this law right here applies only to those springs which are stretched beyond their resting length to a reasonable degree. You cannot stretch it so much that you deform that spring. The spring has to be stretched to a certain degree such that it could recoil back if needed. You have the distance involved, the constant which relates to this spring. Thick springs, thin springs, they have a different constant. How do you go about doing this question? A spring has a resting length of 1 meter. If you were to look at a resting length of that spring, it would be just 1 meter. If 25 newtons of force is needed to stretch it out, if 25 newtons is needed to stretch it out by 0.5 meters, which means when you're stretching it out by 0.5 meters, you stretch it out to a total of 1.5 meters, so you've added 0.5 meters. You need 25 newtons to generate this stretch of 0.5 meters and then to hold it there. And that right there is a useful fact because it can give you your k value. We have two questions. We have to determine the work needed to stretch the spring to 2.5 meters and the work needed to stretch it from 1.5 to 3 meters. And how would you go about doing that? Well, you would have to do this in pieces because the first thing you need is this. The x values over here, the distances are all provided. They are within the question. So let's find that k value because we'll need it. The force is equal to kx, and I know 25 newtons is needed to stretch it by 0.5 meters. 25 newtons is needed to stretch it by 0.5. Remember, it was a resting length of 1, then I'm stretching it to 1.5. That 1.5 total stretch minus the resting length is 0.5. Well, that's your 0.5 right here. K is equal to 25 divided by 0.5, which is 50 right here. The units of this, we don't have to worry about it, but you can figure out what it would be. It would be newtons or meters. Well, I'm not getting into units, but your k value here is 50, and we can put it aside because we'll need it. K here is equal to 50. Now we do question number A, then we'll do question number B. For question number A, we need to know the amount of work to stretch the spring to 2.5 meters. If you have already a spring which is naturally 1 meters and you're stretching it to 2.5 meters, you're not doing a full stretch of 2.5 because you already have a spring which is 1 meters in length. You're doing the difference of the two with regards to the amount of distance involved. And your integral would be like this: work is equal to, you're not going to do here 1 and 2.5. If this right here represents your resting length and you know your spring right here is already 1 meters, if you're going to look at everything from right here, then you could be in error. The better thing is to transpose this over here, because this, after the spring's natural length, would represent your resting length, and then from there you have to do 1.5 meters more, because then that'll give you a total of 2.5 meters. You have to stretch it to 2.5. You don't have to stretch it by 2.5. You have to stretch it up to a distance, total distance of 2.5, of which some of that distance is covered by the natural length of that spring. 0 to 1.5 kx, but I have my k is 50x dx. That right there will give you your answer to question A. You'll integrate this, it's not hard. Bring the 50 out, you're looking at from 0 to 1.5 x dx. You're looking at 50x squared over 2 and then 1.5 and 0. You're looking at 25 times 1.5 square, because 0 is meaningless and it's not hard from here. You have 25 times 1.5 square and your answer is 56.25 joules. 56.25 joules is needed or generated to do this amount of work to stretch your spring up to a distance of 2.5 meters, and you can see this question has been completed. Now question number B. We again have a spring which is its normal length of 1 meters, but we have to stretch from 1.5 up to 3. How would you go about doing that? Well, now what you can do here, remember these lines are not drawn to scale. Think of this as your 0. What's the difference between here to here? It's a 0.5. What's the difference between here up to 3? It's a 2. And that right there will give you everything you need. Here's your 0.5, here's your 2. These are your lower limits and upper limits. The other way you can do it is by this thought process. If your spring is already 1 meters and you have to go up to 1.5, you're doing 1.5 minus 1. That's the start of your interval. And then you're doing 3 minus 1. That's your end of your interval. You're doing 0.5 to 2. And that right there would be your lower and your upper limit, and you would utilize those. Remember, just don't forget the fact that your spring already is 1 meters. You're not doing 1.5 to 3. You're doing 0.5 to 2 in terms of the distance involved, because you have to factor in the basic length of that spring to begin with. Your integral would be this: work, you have this 0.5 to, you have kx dx. This right here you know is equivalent to your force. Work is equal to 0.5 to 50x dx. Not hard. Bring the 50 out, then you do your antiderivative x squared over 2, then you do 2 to 0.5. Now here no limit is meaningless, you have actual limits and you can use them both. You'll have 25, you'll have 2 square minus 0.5 square, and you'll calculate this and your answer will be in joules. You'll have 2 square minus 0.5 square times 25, and your answer will be 93.75 joules. And your question would be solved. Remember, in this video all we've done is look at a single type of work problem, which is to do with springs. We haven't looked at anything with regards to pulleys or changes in the position of an object having certain mass. It doesn't have to be always an up and down movement, it could be a lateral movement. We can do that in a future video, but here we are focusing on springs, and that brings us to the end of this video. Thank you.